So I thank the organizers for giving me this opportunity. As you can see, this talk is basically pedagogic in nature. So we'll be learning about simple pendulum, just simple pendulum. So as you can see that simple pendulum, these are all simple textbook material. This is the equations of motions, etc., etc. In the this is the familiar equation that you learn about, and then the frequency is this. This is constant. This is remember here. This is basically harmonic in nature. And, you get this LC type of equation. But this circuit, this results will not be true if, for example, you do not approximate the sin x with x. So if we consider this to be not x, but you take completely sin x, this is nonlinear, then these equations are not really very easily solvable, and the solutions are given in the book by Sommerfeld, and also some approximate results or the approximations of those results of Sommerfeld in Kittel's book, and also some more better approximations are given by someone called Belendez in 2013. Kittel's approximation, it says that if you increase the amplitude, this here x0 is the amplitude, and the amplitude is very, very small, you can approximate it to a simple harmonic type of thing. But when the this amplitude is large, this approximate result goes like this. Better approximation is this, and the exact result is the following, and this is the one. So if you plot those results, this is the frequency versus this amplitude, they go like this. This is the thing. This is exact solution is this solid line. Belendez's approximation is very close to that, and Kittel's approximation is this. And of course, the harmonic oscillator result, which is just exact, which is this one. The frequency remains the same for all the amplitudes which are really small. This is given in Kittel's book. That this is like this. This is the plot. Now, what is the conclusion? Conclusion is the presence. Okay. So what happens if here? Remember, we are not taking any damping there. There's no damping at all. If you include damping, then obviously this amplitude goes down as it oscillates. These approximate solutions are, of course, given by this European Journal of Physics by Johannesson. Oscillations die out as they move in time. But suppose that you drive, so that means that if when you are looking at just LC circuit, you have got some resonance frequency. You just leave it, and the oscillator will resonate at some particular frequency. But in this case of when the damping is present, there will be it will just die out. So there will be no resonance at all. But suppose that you drive them periodically, then what happens? What you see is that how do you know what is the resonance frequency? In fact, in case of simple harmonic oscillator or other things, when you just include resistance, basically what you see is that the maximum power absorption takes place at the resonance frequency. So we'll take in this case this maximum power absorption as the indication of resonant frequency or resonant power. So the equation of motion becomes this. So remember, if you include the force also, so I have taken this force. This is the potential from there you derive the force. So in the dimensionless form, this is like this. So as you see the potential, this is just sinusoidal. We just see this. So here what we do is that we take this F0 to be small, not very large. If you take this F0 to be large, you will see that the motion of these particles will be chaotic. We will not go into that region. So we will have a small drive. And also we have got this parameter, damping parameter is there, gamma, and this frequency or this period of oscillation. So in this case, we will just find out what will be the resonant frequency of oscillation of a simple pendulum. As a simple pendulum means its amplitude is not really restricted to a small value, but it can have any value. So this analytical solution is really not possible. We have not seen any analytical solution. Remember, this is not stochastic. This is exact. This is deterministic. So what we do is that the program is that we just fix this gamma value, calculate the power absorption for different omega or tau, find tau for which the power absorption is maximum. So that is where the resonant oscillation will take place. Calculate the amplitude of oscillation at that frequency omega 0. Okay. So find. So how do you do is find omega 0, that is the frequency at various amplitudes for different gamma, and plot this omega 0 as a function of gamma 0. This will be just exactly like what Kittel had plotted in his book. So what you find, so this is the final result. This is what you find is that okay, let me see this result. This one is the frequency, resonant frequency for the harmonic oscillator, including damping. And this is the result, this is the exact result, not really exact result given by this. Historically, this result was given by Euler first, and this is shown by. So this is the result, and this one I have given these numbers. These numbers are for various gamma values, various damping parameters, and these points are where this resonance frequency versus x0. For example, I take this gamma value, resonance frequency will be this one, and corresponding amplitude to this. You can see that this one has got a very peculiar character of resonance. Here you can see that this resonance frequency increases very fast, rapidly with amplitude, whereas from here this decreases with amplitude. Whereas there is another region where this is completely discontinuous from there. You just say that this is not continuous with that. This is for drive amplitude 0.2, whereas this one for 0.1. Here the range of these gamma values are different for different regions. Explanation for these ones are also one can see for this one, whereas this one will have a very different explanation. These things, this intermediate range of gamma, this can be explained very easily. Here one thing is very clear, these are numerical results, remember. Here this, when you drive a particle or the simple pendulum, it will not only have some amplitude, but it will have some phase difference with the drive field. Here, this is the phase difference between the drive field. And as you know, that the absorption becomes maximum when the phase difference is pi by 2. Here you can see that the phase difference for these two gamma values, typical gamma values, they behave like this. Phase difference like this. Here, this part is quite usual in the sense that if frequency decreases, then phi, rather frequency decreases, then phi actually also decreases for various gamma values. This is larger gamma, this is smaller gamma. whereas this one is quite unusual. This is completely different, and this happened is just because of inertia. So these things can be explained. I will not go into all this detail. This is for a very large gamma value, where the rise is very rapid, very rapid. However, this part, explanation of this part, this one is quite completely different from that. Here, what happens is that when a pendulum is there, when you drive it with a small amplitude, you see that for the same drive amplitude, you can have two kinds of oscillations, whose amplitudes are, in one case the amplitude is large, in other case the amplitude is small. Not only the amplitude is large, the phase difference between the displacement and the force is also quite large. So here you are just driving the pendulum, but you see that depending on where you start from, the initial condition, you have got two kinds of motion. One, same drive field. One will have a small amplitude, other will have a larger amplitude. And these one, since these only depend on the initial condition, we can explain why those resonance frequency will be different for this. These curves that you are seeing, we have just established one electronic circuit where you find these things. These parts are all, these are just the amplification of these ones. We have just amplified these and we get. Our results, that earlier results, were numerical, but these one are from the electronic circuit. It shows that from the electronic circuit also you can find that these two kinds of oscillations are really there. It's not that this is just numerical. So you can see that these two oscillations, these two states, can be described as a dynamical state, and they have got these various. If you start from here, you go over to the in phase. This one will go to the out of phase. So that when you do it, you have got a mixture of these two phases, out of phase and in phase, where they have got different amplitudes. So you can, there is a region where you see, if you plot in terms of frequency and gamma, you will see that there is a coexistence region here. Both the phases are there, none there. Here there is no distinction. So here, this is the last plot where you have found that here is the frequency versus x0 we have plotted. You can see that as you increase the amplitude, the frequency decreases here. But after some time, this one is just because two phases exist, this just decreases. So this part corresponds to the small amplitude part, this part corresponds to large amplitude part. Large amplitude part, there is a larger dissipation, and this is the line that shows the maximum dissipation. So this line is the one that I showed earlier. So this is what it is. So essential thing is that, let me conclude, and conclusion is that this simple simple pendulum is not very simple. Just a simple pendulum, but you do not know how to calculate the resonance frequency, and you do not know even the relationship between the amplitude and frequency. Amplitude and frequency is entirely very much different. Analytical solution is still elusive. Numerical solution indicate richness of the problem. That means that if you increase the dissipation, you'll see that they behave in a very, very different manner. The applicability of this problem, the prototype, is quite vast. This is just a harmonic, not harmonic oscillators, simple pendulum problem, but it can map to various problems. I'll just go back again. Here it looks, interestingly here, it looks just like a density pressure diagram of this liquid gas system, where this is the coexistence region, this is only the liquid phase, this is only analogy. There's nothing more than that. Thank you.
Any questions? Yeah.
Mangal, did you also look at what happens when you actually put in a noise? That's number one question. And also, if the frequency of the drive is very large, one might think that it's a very difficult problem, but there is something called Kapitsa region where you have an averaging out and you get an effective potential for the sine of x. Did you look into those regimes as well?
This is the regime. This is the regime where the frequency is very, very large. You can see that the amplitude becomes very small. So the system is unable to respond there. So if the frequency is very large, it doesn't respond at all. Here you can see that the amplitude goes down very, very fast. And of course, if you include noise also, I have not calculated the resonance frequency, but here you can see that if you include the noise, you can see that this is basically Poincare plots. They do not become just point; they just spread out. And if you increase still further, this is not stochastic resonance. This is not stochastic. This is just resonance.
Any questions? Okay, if not, let's thank speaker.